Today we're going to have a look at logic operations in MIPS. Now you'll be familiar with a lot of these, your ANDs, your ORs, your NORs, your XORs, all that sort of jazz. Today we just want to see how they apply to 32-bit words, half words, bytes, and why we might want to use them in a MIPS setting. So let's have a look at what we've learned so far before we start on logic instructions. So we have quite a lot of the loading and storing down by now, or at least you should. For arithmetic we have all of these instructions, or at least I would expect that you should be able to use these in the right context and given the MIPS summary sheet. We haven't used divide, for example, in any of the videos, but it works in much the same way as multiply, so it shouldn't be too tricky to pick up. So let's have a look at what we're going to add to this list today. These are the logic instructions. Now you'll be familiar with a lot of these. The only sort of MIPS specific thing we have here are the immediate equivalents, and they are very similar to your add immediate. You just get one register and you specify one hard value in the immediate section, and you apply the logic instruction with that value. So there shouldn't be anything too tricky here, but we'll have a look at why we might want to use these. So these apply to each bit in a pair of words. So if we use AND, for example, we apply AND to both of the values in the ones column, both of the values in the twos, then the fours, then the eights, and so on. So we compare it to the corresponding value in the other words. Now that's going to be a little bit trickier because we're quite often used to just using AND with one value, but we're going to be applying it bitwise for a whole 32-bit value. So in high-level languages we have logical operators, we have our ANDs or ORs or NOTs, we have bitwise operators, but in MIPS we only have bitwise instructions. We don't have anything that applies any other way. So let's have a look at AND and why we might want to use this. So let's have a look at this instruction where we load an immediate value of 5555 into T0, and then we want to AND immediate that with OFC3. Now that might sound weird because these are hexadecimal values and we're not really used to doing this with hexadecimal values. At least I thought it seemed weird when I first saw this. But what we can do is we can just convert these to their binary form, and there it makes a lot more sense. And you can see the result 0541 corresponds to the binary word where the 1 is set only when both of the original values have a 1. So we both 555 and OFC3 have a 1 in the ones column, so we get a 1 in 0541. So you should be able to tell this is just AND bitwise extended over 32 bits. That's all, nothing more. So let's have a look at one use for this. A very useful way to use AND is for a parity check, which is to say to test whether a word is even or odd. So if we use this instruction, AND immediate, we store the value in V0, and we're comparing A0 with the value 1. Now if the 1 is set, then that means that a number is odd because everything else is even, so if you add a 1 to it, it will become an odd number. So what this means is, if A0 is even, then the V0 register will store 0 because there won't be a 1 in the ones column. If A0 is odd, then we will get a 1 in the V0 register because there will be a 1 in the ones column in A0. So this is a simple way to test to see if a number is odd or even. And we can extend this further actually, so we can determine whether a particular bit is set by specifying the hexadecimal value that corresponds to that bit being turned on. You can see in this example we've used 04, that byte 04 means that there is a 1 in the 4s column. And if we AND this with A0, we'll get the same result as before, where if the bit in the 4s column is set, then V0 will be 1. And if it isn't set, then it'll be 0, and that's because we're ANDing it with the hard set value. So we can tell if a specific bit is set using the AND instruction. And in fact we can even take out particular bits from a word if we're so inclined. If we specify the bytes that are the bits that we want to take out by giving the hexadecimal number which corresponds to having these ones set, and we AND it with a value, it will pull out whatever of those bits are set in the word in A0. So you see this quite a lot when we did 106, and for the CES students you'll likely have seen this trick before, where if you AND a value where one of them is 1, the result is whatever the other one is, because if it's a 1, the other one is already set, so we return the 1. If it's 0, the AND fails, and we return a 0. So this is quite a nice way to extract a little bit more information than you might think you're able to acquire by using AND in a clever way. You can clear selected bits as well by doing the opposite and setting 1 in every bit that you want to keep and setting 0 in the bits you don't want to keep. So in this example we have set the third and fourth bits of a word to be 0, and that will mean that in the word that's in A0 the AND will automatically fail because one of them is going to be 0, and so the word that's stored in A0 afterwards will have those 2 bits set to 0. So this is just the opposite of what we've seen previously, but again it can be quite useful to do things like this. Okie dokie. OR is very similar. OR returns 1 whenever one of the bits or both of the bits are 1. So the only time OR ever returns 0 is when both of the values are 0. So you can see here we're loading in the value of 5555 again, and we're ORing it with OFC3. And again, if you convert it to your binary representation, you can see the word that we'll get out at the end here. And it might again seem weird when we're doing this with words, but I really want you to keep in mind that these are actually binary values that are just being represented by hexadecimal values. And we can use this to set selected bits. Because we know that OR with at least one value of 1 will return 1, if we set 1 in the columns that we want it to be 1, in this example we've set 3 to 6, that'll mean that in the resulting word in A0, the 3 to 6 bits will be set because the OR is already going to succeed because of the value that we've given it. So another way that this is used is the pseudo instruction load immediate uses OR, because load immediate is not an actual instruction, it's a pseudo instruction, and we saw this in one of the earlier videos, but we didn't dive into the two instructions that make it up. So if we look at this, if we're loading immediately this word 13579BDF into T0, the assembler doesn't actually just do that. It splits that up into 2 instructions and then carries out those 2 instructions, and that becomes load upper immediate into the register AT using 1357, so that's the upper 16 bits, they're loaded in, and then we OR that value with the lower half, and we know that the lower half is going to be retained because OR only needs 1 bit to be set, so the bits that are set in the lower half of the word will automatically succeed and they'll be set in the result. So that might be a lot to think about, but I'd like you to spend a little bit of time thinking about this just so you can get it straight in your head. Again, you're welcome to ask me questions at any time, but anyway, moving on, we have exclusive OR. Now exclusive OR is kind of like a toggle in that it returns 1 only when one of the bits is 1. It doesn't return a 1 when both are 1, and it doesn't return a 1 when both are 0. So let's have a look. Again, using our 2 example words here, you can see the result is only 1 when only one of the words has that bit set. So when would we use this? Well, we'd use it to toggle. So if we give it a hard-coded value with some 1s set, so some bits that we want to toggle set, in this case it's the first 3, the bits 0 to 2, then the word in A0 will be 0 when it has a 1 in one of those columns, and it will be 1 when it has a 0 in that column, so that it'll be whatever it has in there, it will be flipped, and that's what we mean by toggling. It's not like a toggle flip-flop, thankfully, it's just swapping the values around, or in essence negating in a way, but only the bits we want to negate, so that can be quite useful for you as well. So let's have a think about when this might be useful. So let's say we want to write some code to place into V0 the remainder when A0 is divided by 8 using logic instructions, and we have all of these available to us. Now at this point in the video you might want to pause it, have a wee think about it, and come back before I reveal the answer. Otherwise I'm going to reveal it and have a little bit of analysis about how that is the answer. So this is how we do it. We AND immediately with the value 07 using whatever is in A0 and storing it V0. Now this might sound counterintuitive, but remember if we have an 8 in the first column, then we can divide any number that is a multiple of 8. So the ones below that will be the remainder. So let's think about this in more detail. When we divide a number by 1,000, then we just take whatever is lower than 1,000 and say that's the remainder. So in this case, when we have 56,789, we know that that is going to be divisible 56 times by 1,000, and the remainder will be 789. In the same way, when we're doing binary, the remainder will be the first 3 bits, because we know that the 4th bit is going to be the 8. And any number that's divisible by 8 or multiple of 8 will be able to be created by everything that follows on. So for example, we have the first multiple of 8 is 8. So if the 8th bit is set, or the bit in the 8th column is set, then it will be divisible by 8. If the 16 is set, it's divisible by 8. If we have 24, then that's 16 plus 8. And if we have 32, that's the 32's column. 40 would be 32 and 8. 48 would be 16 and 32. So really it's just the first 3 columns that we care about. That's the only bits that are going to produce a remainder in this example. So we just take those out by ANDing immediately and setting the first 3 bits to be 1, and this will return 1 when those bits are set, so we'll find out what the remainder is from those first 3 bits. This is a little bit of a tricky one. I'd advise you to think about it and get it into your head in a way that makes sense to you. But that's everything for today. I hope you found this useful. If you have any questions, please do let me know. Thank you.